Morning, everyone. Welcome to the webinar on how AI is transforming semiconductor manufacturing from a physics perspective. That means from the physics of view. Okay, today we are at an exciting intersection between the semiconductor physics and also the data-driven power of artificial intelligence. Or another way is we are calling it as a AI. So many years, the semiconductor industry has been guided by the Moore's law and the continuous drive to make a chip smaller, faster, and more powerful. But as a result, the modern chip now contain the feature measured in a single-digit nanometer. That means it's just only a few atoms wide. So at this extremely small scale, classical manufacturing, the rules start to fail. And the behavior of a device is increasingly governed by the quantum mechanics and also the electromagnetism. So traditional inspections and the process control method is struggle to handle this level of complexity. So that is why physics-driven AI becomes very important. And instead of only analyzing the data, this new approach will integrate the physical law into the AI model to better understand how the light, material, and also the energy behave at the atomic scale. So in today's webinar, we will look at how these combinations, the AI and the physics, is transforming the semiconductor manufacturing from the device design to the defect detections and enabling the next generation of semiconductor. Okay, now to guide you all go through the landscape, I will start with define what is the physics-driven AI. And here I will explain how we move away from the traditional black box AI model, which can be give an answer without explanations toward the system that are interpretable and grounded in a scientific principle. And we will touch upon the core physics concept like the Maxwell equations and the quantum mechanics that are begin embed directly into the machine learning algorithm. Next, we will look at some specific applications. Start with the intelligent defect detections, and you will see how the advanced AI model can detect a very small defect and even identify their root cause, thing that the old method cannot see. So I will then move to the advanced lithography patterning, the heart of the chip making, where the AI is achieving precisions at the Amazon scale, which are smaller than a single atom. Following that, we will look at the etching and depositions, showing how the AI will be control the plasma dynamic with atomic level precisions. And we will also cover process control and optimizations, where the AI is transforming the statistical monitoring into the predictive intelligence system and also boost the yield and efficiency. And finally, we will look at the future of manufacturing, where the generative AI can help design the new material and self-driving a laboratory can speed up motivations. The semiconductor industry is facing a big or huge challenges. As we move to the chip smaller than 5 nanometer, the old optical model and the traditional rule no longer work. So the modern 3D structure like the gate all around and the FinFET, it involve hundreds of the process steps and also the thousands of interconnected parameters. So at this tiny scale, where we need a precise model than an atom, conventional process control cannot handle this type of the complex physics involved. Many years, manufacturers have used statistical process control. But at this chart, if you look at the chart, you will know that traditional SPC reacts slowly and often give a false alarm with a complex data. Today, factories have thousands of interconnected and non-linear parameters. So the single variable charge are not enough anymore. So we need a system that can be understand the complex physics and make the real-time decision. So something the AI is perfect for. So what is the physics-driven AI? This is the AI that built on the law of physics. By combining the data with a scientific principle, these models are more accurate and easy to understand. They also avoid unrealistic predictions because physics is guide the system. And in short, it also will bring together the century of the physics knowledge with the power of modern AI. Okay. Let us take a moment to visualize what difference between the traditional data-only AI model and the physics-informed one. A traditional model, normally we are called it as a black box. So we feed the data. So in this case, thousands of the sensor reading and the wafer image. So it will produce a predictions. It's learned to recognize the pattern, for example, and a certain temperature profile and lead to the defect. However, this has no real understanding of why, because it does not know about heat transfer, material science, or electromagnetism. This work will well if the future look exactly like the past. So in the new parameter is introduced or unexpected situation happen, the model fail spectacularly. So sometimes making predictions that are physically impossible. I just give you an example. If let's say a student only memorize the answer for the test or exam, but cannot solve a real new problem that require true understanding. So right now, the contrast that with a physics-grounded architecture. So this model is not just a train on the data. It's also taught the rule of the game, the law of physics. So as you can see in the diagram, okay? Fundamental equation like the Maxwell equations, which as describe how the light, electricity behave, are embedded directly into the AI structure. So this means the AI learning process is guided and constrained by this law. It cannot make a predictions that violate the principle of the physics, and this makes the model for more reliable, especially when you extrapolating to the new conditions. So it can be make accurate predictions even with a less data because it can be fill in the gap and using its knowledge of physics. So this transform the AI from a simple pattern maker into the interpretable and trustworthy partner for the engineer. So what is the specific physics principle are we embedding into this AI model? Actually, there are three main pillars that are critical for the semiconductor manufacturing. The first is the electromagnetic optic, governed by the Maxwell equations. So these equations, they are the foundation of how we understand the light. And in the chip manufacturing, this is absolutely needed for lithography and the process of using the light to print the circuit on a silicon wafer. So by embedding the Maxwell equations, and the AI can be accurately simulate how light wave will be bent, interferes, and interact with a complex multi-layer material on the wafer. And this to ensure that the pattern we are intend to print on the pattern we actually get. This is also crucial for modeling the plasma using inner etching processes. The second pillar is the quantum transport, which will be explained by the Schrödinger equations. As the transistor have reduced to the atomic scale, so the behavior of the electron is no longer governed by the classical physics, but by the strange rules of quantum mechanics. So these Schrödinger equations allow the AI to model how electrons move or transport through these tiny nanoscale devices, including the quantum phenomena like tunneling, and this is essential for accurately predicting a chip final electrical performance. Okay, the third pillar is a thermodynamic constraint. That are the law of the energy conservations and entropy. They govern everything from the stability of the material during the high temperature process to the chemical reactions that will be occur during the deposition and etching. So before enforcing this constraint, the AI will be avoid making unphysical predictions, like suggesting a process that will be violate the law of conservation of energy. And by integrating this core principle, we will create an AI model that are not only data-driven, but also the science-driven, leading to the remarkable 40% reductions in the error when predicting outcome for new processes. The key technology that connect the deep learning with a physics is called physics-informed neural network. A pin will be combined a neural network with a physical law. Instead of learning only from the data, the model is also trained to follow the physics equations such as Maxwell equations. And this means that the AI must be both fit the data and follow the law of physics. So as a result, this can be made more reliable and realistic predictions even when the data is limited. Something very important in the semiconductor manufacturing. Okay, now let's look at our first applications, lithography. Lithography is one of the most important steps in the chip manufacturing. The main challenge is to achieve extremely high precisions when the chip structure becomes more complex. So today the manufacturers aim for accuracy at the sub-nanometer level, so which is smaller than about 10 atom wide. So at this scale, even the tiny error can affect the device performance and will be produced and will production's yield. We are operating very close to the limit of optical physics. AI help improve precisions beyond what traditional method can be achieved. At the Armstrong scale, we face the huge physical challenges. Traditional model no longer work because of the optical limit. Signal become very noisy, especially when measuring the tiny surface roughness. So the near field defect is like the light scattering from the surface, make it even harder to get a clear measurement. So at this 1 nanometer scale, conventional tools fail. We need an AI-driven approach to overcome this limit. This challenge becomes even harder when we are moved to the complex 3D chip design. Technologies such as gate-all-around transistor and the 3D flash memory add a lot of structural complexity. And this device include very small nanowire channel and the feature below 3 nanometer and a memory cell stacked over the 100 layer high. So with so many material and the layer, the light scattering in a complex way. Because of this, it's become very difficult for the traditional optical tools to maintain the accurate pattern deep inside this structure. Okay. Engineers will use the AI-powered inverse lithography technology, or we call it as a ILT. A technique will be used to improve the pattern accuracy in the lithography. Because of the optical diffractions, the pattern will print on the wafer is often different from the mask design. So the inverse lithography technology will solve this by working backward. So the AI will be start with a desired final pattern on the wafer and calculate the best mask design needed to produce it. So this AI-based method will help compensate for complex light effect and also will reduce the mask design cycle and improve the precision needed for advanced chip. Deep learning model like the convolutional neural network and transformer are at the heart of the modern mask optimizations. So by training this all huge data set of pattern mask pair, this AI model will learn the complex and nonlinear relationship between the desired wafer feature and the required mask geometry. So the result is a massive accelerations in the design time, generating the optimized mask in a millisecond instead of hour. So this breakthrough has a direct impact. Allow 60% reductions, repeat the cycle, and accelerating the time to the market for advanced 3 and 5 nanometer process node. To make sure the AI design masks are physically correct, we use a physics-informed neural network, or we are calling it as a PIN. A PIN training has two parts. Check how well the prediction match the data and check how well the prediction follow the Maxwell equations. So by including the physics in the training, the AI will learn how light really behaves and making its predictions more reliable, even in a new or unusual lithography condition. Okay. AI is also very good at handling complex optical effects that are hard for the traditional method. At the nanoscale, the factor like the light polarizations and the interference between the layers will become very important. AI can predict how the light behaves as it passes through the 3D structure and the multiple material layer. For example, ASML company will use the AI enhancement modeling to reduce the mask design time by 40%, while improving the accuracy of the pattern in the advanced EUV lithography. Next, let us look at the etching and depositions. When the goal is atomic level precisions, AI will be control the complex plasma behavior and surface reactions inside the chamber. So by combining the physics model with a machine learning, it can be adjust the process parameter in the real time. So this allows the uniformity at the atom scale across 300 nanometer wafer. So the AI can monitor surface reactions and adjust the plasma setting to keep everything within the Armstrong level accuracy. Traditionally, plasma control use the fixed recipe and try and error tuning. AI changed this into the smart dynamic process. By combining the model of the electromagnetic field and the surface chemistry, the AI can adjust the power, pressure, and gas flow in the real time. So this approach will be reduce the defect by 38% and adapt to the tools while the chamber aging and keep the atomic level uniformity across all wafers. And one powerful method used here is reinforcement learning, RL. Reinforcement learning agent is learn the best way to control the process by try and error and improving over the time, unlike the statics model. So it's adapt continuously. For example, Samsung showed that the RL can reduce the uneven etching by 38%. So by adjusting the plasma setting in the real time, the RL agents create a uniform etching and automatically compensate for the AI for the tools etching. To find the best process setting, we use the Bayesian optimizations. Instead of testing every possible combinations, this method is smart explore the most promising option. Is build a probabilistic model of the process and choose the next parameter to try. So this approach can be cut experiment by up to 75% and saving energy, improving yield. So something Samsung has successfully demonstrated. At the atomic level, etching and depositions will be involved very complex surface reactions. AI model, especially recurrent neural network, like a LSTM, can learn how these reactions change over the time. So by training on the real-time spectroscopy data, the AI can predict the reactions pathway. So this will let the system adjust the gas flow and also the power dynamically. Keep the etch profile optimized and reducing the defect like micro trenching and bowing by 42% in the advanced 3D fabrication. Okay, now we look at the real-time monitoring of an etch profile. AI-driven modeling allows the real-time control of an etching and deposition process. By using this live data from the tool, for example, like FTIR spectroscopy, With a LSTM model, the system can track how surface reaction change over the time. And this will let the AI predict and prevent problems like micro-trenching and profile distortion before they happen. So automate adjustment to the gas flow and other settings is based on these predictions achieve a 42% reductions in the micro-trenching effect. AI also transforming the thin film growth, such as atomic layer deposition. Precise control of the thickness, stress, grain structure is essential. The deep learning model can predict the best temperature, pressure, and percussion flow to achieve the desired film property. For example, graph neural network can predict the grain boundary formations with a 0.93 correlations to the experiment. So this will enable the real-time stress monitoring and prevent the film cracking and ensure the atomic level thickness control across the wafer. Graph neural network are the particular powerful tool for the film characteristic. A GNN treats the atomic structure of the film as an interconnected graph and allow to predict the property like the grain boundary, formations, and also the surface roughness directly from the deposition parameter. So if you, let's say you see from this deposition, this thing, the GNN can correlate the process conditions with the resulting film crystalline quality. So the model will be developed by the IMAC, achieving an incredible 0.93 correlations with an experimental result and revolutionizing our ability to predict the growth film with a specific characteristic. Okay, now we look at the defect detections and inspections. At the sub-5 nanometer scale, traditional optical method cannot see the critical defects. AI, especially computer visions, can automatically detect and classify this defect with a much higher accuracy. So by analyzing the data from the tools, for example, like the optical and the e-beam scanner, AI can detect the problem in a real time, preventing costly failure. Catching a single defect early, it can be saved the entire wafer. Okay, the two main AI models are used for defect detections. First, convolutional neural network, CNN, and vision transformer. So the CNN are the great at recognizing the local pattern, analyzing the feature layer by layer. For the vision transformer, they are using the cell attention to understand the global content and also the long relationship in an image. So by combining these both, AI can be achieve a very high precision. For example, in a 3D structure, and this model can reach 98.7% classification accuracy. Okay, the strength of the vision transformer is their cell attention mechanism. Unlike the convolutional neural network, which focus on a very small area, the vision transformer can look at the whole wafer image and detect the pattern over the long distance. So this will help them to find a spatially connected defect or substance cluster that other methods may miss. So when using a vision transformer, defect detection in a 3D structure reach 99.1% accuracy. And overall, the yield prediction will be improved by 50% by spotting the cluster that will be previously invisible. A major challenge in the defect detection is need for thousands of label samples for each new defect. Few-shoot learning using the vision language model changes. It can be achieved a high accuracy with a 5 to 10 sample. For example, in the Cosmo Reason study, a new defect can be classified with a 96% accuracy just using the 8 image only. So this will greatly speed up the model development. This breakthrough of a vision language model, like the Cosmo Reason, is that they can connect the AI detections with a human understanding. The AI does not just spot the defect. It will be explained in the plain English. For example, center ring defect likely due to the chemical contaminations. So this will turn the defect analysis from the simple pattern identifications into the root cause understanding. So engineer can ask, why did this defect happen? And get the scientifically based answer to guide quick corrective action. To make this system even more powerful and adaptable, we use a foundation model and a self-supervised learning. If you are look at the workflow here, we start with a model retrained on a million of general image, and we then adapt it to our domain using the million of unlabeled image from the fact. Finally, we are fine-tuning it with a very small number of label samples. So this approach is where you using the model like the NV Nino has boosted the accuracy from the 94% to over 98.5%, while cutting the develop time in half. The real-world impact of the AI inspection is huge. NVIDIA AI system has reduced the false alarm by 40%. So the engineers spend less time changing the relevant issue. And the modern development is twice faster, and the system can monitor the defect in real time and increasing the production speed. For example, manufacturers were using the NVNino model will reach 98.5 defect accuracy, up from 93.8% with a traditional method. Let's look at the process control. Traditional SPC was reactive and focused on one parameter at a time. And this is not enough for today's complex fab. AI-powered SPC, they can be detect multiple parameters and predict the problem before they happen. So it's much more proactive and reducing the false alarm by up to 99%. Two powerful AI framework for the modern SPC are the LSTM network and autoencoder. LSTM excels at modeling long-term temporal dependency in the sensor data. It allows them to detect greatly processed rifts that are invisible to the traditional chart. Autoencoder will learn the repeat normal process behavior in a small, complex form. Anything that does not allow the normal pattern is remarked as unusual. So this method can be spot the new problem that haven't been seen before and cut the false alarm by 40%. The main benefit of unsupervised method like autoencoder is like they can spot a new unseen problem without any label data. Unlike the rules-based system that needs set the threshold, this AI model automatically will detect unusual pattern in a complex sensor data in a real time. So this works as a yearly warning system. They will be catching the substance change, like shifting in a power usage that the signal to wear. So it's also allowed preventive maintenance and is help avoid costly unplanned downtime. A part of trusty AI is explainability. We use the tool like a shark to show why the AI make a decision. For example, it can be revealed which input, like to change in the gas flow, will cause an instability. So this will turn the black box predictions into the clear, actionable insight, so the engineer can take the right corrective step. One of the most important use of the AI is predicting and optimizing the yield. AI can forecast the final wafer yield very early in the productions with a high accuracy, the R-square value above 0.95. For example, Infineon will use the deep neural network on a 7nm process data and achieve an R-square of 0.96. This let the engineers spot the low yield batch early and take actions, boosting the profitability and reducing the waste. To make the accurate yield predictions, we use a different machine learning model. Traditional models like the random forest are easily to interpret and reach R-square around 0.89, while the XGBoost can go up to 0.95. So for the model complex fed with 1,000 of variables, the deep neural network is the best. We can improve the further with a physics-informed DNN, which include the thermal, stress, electromagnetic factor from the simulations. So this hybrid approach will boost the accuracy to the R-square 0.97, setting a new standard in the yield predictions. The most accurate yield predictions come from the hybrid model that combine the machine learning with a physics-based simulations. The data-driven AI will find a pattern, but does not understand the physics. While the pure simulations are accurate, but slow and miss the real-world variability. So a hybrid model, they will be combined the two. Simulation of the thermal gradient, stress, and material behavior are fit into the AI as a feature. This will give the model a deeper understanding of the process, making predictions scientifically valid. So using this approach can be improved the R-square, the yield predictions from 0.94 to over 0.97, and showing how the combining AI with a domain knowledge deliver superior result. Predicting yield is useful, but the real goal is to control it. It will be done with a closed-loop AI, which continuously monitor the process, predict the outcome, and adjust equipment in the real time. Sensor track key variables like the temperature, pressure, gas flow. The AI analyzes this data predict effect on yield, and calculate the optimal adjustment. Not just boost the yield, but also the save energy and reduce equipment wear. This system adapts constantly. For instance, it can be treat plasma power if it detects a drift that could be lower the yield. So this approach has shown a very strong result. Energy will use drop 80%, while the yield will be increased 1.7%. So it demonstrates how the AI improves the both efficiency and the performance. One powerful tool from the physics-driven is a digital twins, a visual high-accuracy copy of the real factory or the process. In a semiconductor manufacturing, it's a mirror the entire wafer fab, update with a real time with a sensor data from the physical machine. Unlike a static 3D model, the digital twins will use the physics-based simulations to model how processes actually behave. So the engineer can safely test the new recipe, material, or the equipment setting in this virtual environment. It predicts the effect on the yield, equipment wear, and without risking the real wafer. So this approach speeds up the development and also allow the thousands of virtual experiments, reducing the physical test by 60% and improving the process accuracy by 25%. A big future opportunity for the AI in a semiconductor is designing the new material. Next generation transistor need the material with a special property, high K dielectric, to reduce the leakage or the 2D material like the graphene that could be replaced silicon. Traditional discovery is slow. Take months or the years of try and error. AI can change this predictive inverse design. Instead of searching randomly, we define the property we want, like the certain band gap or the thermal conductivity. And the AI will work backward to create the new material that match those properties. This generative model can explore the countless atomic structure, propose the stable, never before seen material. So this approach is already speed up the discovery of the high K dielectric, 2D channel, and the new semiconductor alloy, cutting the time for innovations dramatically. Generative AI can create a new material using the advanced model. One method, diffusion model, train the AI to turn a perfect crystal into the random crowd of the atom and then learn to reverse it. Once trained, the AI can start from noise and generate entirely new realistic crystal structure. Another method, GFlowNet, the sample structure based on the reward functions that favor desired property like stability or a specific band gap. This work in a practice, for example, the AI model MetaGant will be design a new material, predicting it will be stable at a high resistance to the compressions. So when the scientists make in the lab, the predictions was correct. So this is show that how AI can quickly turn data into the new material design, helping the scientists find a promising candidate for the next generation electronic. When the AI design the new material, it must be follow the law of the physics. Without this, it could suggest structure that look good on the paper, but impossible in the reality. So the physics-informed machine learning solve this problem by embedding the physics rule into the AI. For material, this means enforcing key constraints, crystal symmetry, thermodynamic stability, conservation of energy, and also the electronic structure. So by guiding the AI with this rule, it only will explore the reality material and reducing the error by 40% compared to the standard AI, and making the material discovery fast and more reliable. To get a complete picture of new material, we use the multimodal learning, which the fuse data from diverse analytical technique. AI model will integrate the X-ray, SRD data for crystal structure, SEM, scanning electron microscope image for morphology, and spectroscopy data for chemical compositions. So by combining these different data streams, cross-model neural network, for example, like the SAGNN, it can be achieve a holistic predictions of the material behavior, predicting the property like formation energy with a very extremely high accuracy. Eventually, AI is enabling the next industry revolution, Industry 5.0. The goal beyond a connected factory to form a smart coordinate system. As you can see here, AI integrate with an intelligent robotic, IoT sensor network, and the edge computing to create a unified and self-optimizing system. Modern fab with 100,000 sensor and 500 robots, they are reaching 99.7 uptime, and thanks to the AI-driven automations. AI and robotics are creating the self-driving laboratory. In this lab, the AI will propose the experiment, robot will carry them out, and the sensor will give an instant feedback. The AI then will analyze the result and plan the next experiment. So this allows fully automation, 24/7 operations, and cutting the discovery and optimization time from months to days without human interventions. In a complex global supply chain, data integrity is crucial. We use the blockchain to record every process step, material batch, and the AI model versions as an unchainable record. So this will be ensure the full transparency for enforce and quality check, and allow the different fab to train the AI together, securing without sharing their raw data. Even with a progress, the data is still the main challenge. Quality data is limited, inconsistent, and shallow across the fab. To solve this, we use a generative model like the GAN to create the realistic synthetic data and federate learning to let the multiple fab train the shared AI model without sharing their private data. We must also address the environmental impact. Training a single large AI model can have a significant carbon footprint equivalent to the car lifetime emissions. The industry is actively pursuing mitigation strategy. This includes the compression model using the energy efficient hardware like TPU, running the data center on a renewable energy. The tools like the cold carbon are more emerging to help us monitor, manage the energy consumptions of our AI workflow, and to ensure our progress is sustainable. Looking ahead, quantum AI is emerging. Quantum machine learning can solve the problem that classical computer cannot. Using the algorithm like the VQE, we can simulate the electron behavior and calculate the energy of a new material with a high accuracy. This will help discover the material with a precise bandgap, thermal property, and create a feedback loop that advances both quantum and classical computing. In conclusion, AI is not replacing human expertise in a semiconductor manufacturing. It is enhancing it. So by combining the AI with a physics, we create a reliable system that will turn the manufacturing from the reactive work into predictive science. So the future of semiconductor manufacturing will be intelligent, sustainable, and physics-driven. By merging the AI data-driven intelligence with a physics fundamental law, we can make the semiconductor manufacturing smarter and more efficient. AI can analyze the massive amount of the process data to detect the pattern and predict the outcome. Well, physics is ensure these predictions follow the real-world rules of material and energy. So together, they allow us to optimize the process, reduce the defect, and improve the yield, while also finding the innovative way to push the past physical limit. These collaborations is not only enhance the current productions, but also unlock the new probability for the next generation semiconductor technology. The end. Okay, for those companies who are looking for the industry-focused semiconductor training, you can be directly contact me to discuss for the suitable program. Okay, all the semiconductor trainings will be fully under HRD Corp claimable. And beside that, myself is also seeking for the postgraduate student, master or PhD. So if you have a semiconductor or the physics related factory project and you wish to develop it into the master or PhD research, please contact me for the brief. Will have a brief discussions. If let's say your company, you have a one group of the pupil, then you can send me an email. I can walk in your factory to give the full detail, okay? Since the webinar is scheduled for the 1 hour, so if you have any question, you can send me the email directly.